Ever wondered about the hidden patterns in nature and numbers? From simple to complex, sequences and series offer a fascinating journey through the world of mathematics. Do you want to explore the creative side of mathematics with sequences and series? Are you ready to think outside the box? Then join me on this mathematical adventure. Welcome to today's lecture on sequence and series. This fundamental topic is a cornerstone of mathematics and is widely used in various applications such as finance, physics, and computer science. Sequences and series are powerful tools for solving real-world problems. From calculating compound interest to analyzing algorithms, they provide insights into patterns and summations. A sequence is an ordered list of numbers, and a series is the sum of these numbers. Both finite and infinite versions of sequences and series exist. These concepts extend to arithmetic and geometric patterns, factorial notations, and sigma notations. Historically, sequences like the Fibonacci sequence have been studied for centuries, originating from applications in nature and architecture. The concept of summation has grown through calculus and mathematical analysis. So we've already defined what sequences and series are, but let's just do a refresher. A sequence is a function whose domain is positive integers, and a series is the sum of sequential terms. Now, arithmetic and geometric sequences. Here is something that you can use to differentiate them. For arithmetic, it has a constant difference between terms, while geometric has a constant ratio between terms. So we're also going to touch on factorial notation and sigma notation. We will explore each type of sequence and their respective summation methods with solved examples for better clarity. So this couple of examples we are going to be looking at, like infinite sequence example, factorial notation example, and arithmetic sequence example. So we're also going to find out how to find the nth term under arithmetic sequences, and we're also going to find out how to find the sum using the summation formula. We'll also find out how to get the nth term under geometric sequences, and we'll also find out how to find the sum using the summation formula for the finite series case and also for the infinite series case. For the questions we are going to be solving during this tutorial, we're going to group them into three stages: simple, medium, and hard. And don't forget, hard in this case does not necessarily mean impossible or difficult, but just slightly more challenging than the other questions we're going to be solving. And the solutions are going to be detailed step by step. Understanding infinite series convergence can be tricky for beginners. Real-life applications sometimes require approximations. While sequences are easy to represent, their analysis often demands higher order thinking skills. So as for current trends, sequences can be applied in areas such as computer algorithms, cryptography, and machine learning. And for future research, sequences and series can be used in exploring nonlinear sequences and hybrid progression types in data modeling. By the time we're done with this course, we would have explored the definitions, the types, and applications of sequences and series, focusing on arithmetic and geometric cases and so many other examples like summations, factorials, Fibonacci sequence, and so on and so forth. And we would have reinforced the concept behind sequences and series, forming the mathematical foundation for practical and theoretical fields. And we'll also look at real world applications so that we can really and truly understand their significance. We'll also have a session where we will address any unclear points and discuss specific examples. And we're going to address concerns and tackle both fundamental and complex queries. So at the end of it all, I'm going to be giving you two questions on each segment we are going to address so that you can go back and practice, and you can always go back to the former examples we treat so that you can make sure you understand every concept we are going to touch throughout this tutorial. And hopefully, I guess that is all when it comes to this tutorial. Any other information that I feel might be necessary for you to know will be communicated to you in due course. Thank you. and God bless you. So let's dive into the world of sequence and series. In mathematics, the word sequence is used in much the same way as in ordinary English. Saying that a collection is listed in sequence means that it is ordered, so that it has a first member, a second member, a third member, and so on. Two examples are 1, 2, 3, 4, and 1, 3, 5, 7. Mathematically, you can think of a sequence as a function whose domain is the set of positive integers f of 1 is equals to a1, f of 2 is equals to a2, f of 3 is equals to a3, f of 4 is equals to a4, equals to f of n is equals to an. Rather than using function notation, however, sequences are usually written using subscript notation as indicated in the following definition. An infinite sequence is a function whose domain is the set of positive integers, the function values a1, a2, a3, and so on up to an and so on are the terms of the sequence. And if the domain of the function consists of the first positive integers only, the sequence is a finite sequence, that is a1, a2, a3, and so on up to an being the last term. So let's look at some examples of sequence. For example, seating arrangements. The number of people that can sit around a table or the number of seats in each row of a stadium are examples of sequences. Stacking. The number of objects compared to their height when stacking cups, chairs, or bowls is an example of an arithmetic sequence. Filling. The amount of water in a sink or pool as it fills is an example of a sequence. Fencing. The number of fence rails needed for a fence is related to the number of posts. Saving money. The amount of money saved at each interval when saving money in equal installments is an arithmetic sequence. Traveling. The amount of petrol left in a car's tank while traveling at a constant speed is an arithmetic sequence. Population growth. The rate of change of a population is an example of a sequence. Spread of a virus. The spread of a virus is an example of a sequence. Investment growth. The growth of an investment is an example of a sequence. Depreciation. The depreciation of an object is an example of a sequence. Compound interest. Compound interest is an example of a sequence. So we're going to start from the beginning with the simplest concept, which is writing the terms of a sequence. And as you can see, we're given two examples here. Write the first four terms of the sequences given by a n is equals to 3n minus 2, and b, an is equals to 3 plus, in brackets, minus 1 raised to power n. So as you can see, the first one is solved here, and we are also going to solve that on the whiteboard. So maybe I should skip to the next question. For the second one, the first four terms of the sequence are given by a n is equals to 3 plus minus 1 raised by n. Since you are looking for the first four terms, all you have to do is just substitute 1, 2, 3, and 4 into n, and you are going to arrive at your respective answers, which in this case is 2, 4, 2, and 4. So back to the A example, we are told to solve an is equal to 3n minus 2. So this is under writing the terms of a sequence, and it's actually very easy. Since we are asked to look for the first four terms, all we have to do is substitute 1, 2, 3, 4 into n, and you are going to arrive at your sequence, the first four terms of the sequence. So for a1, when you slot in 1 into n, you are going to have 3 times 1 minus 2, and we know that 3 times 1 is 3, and 3 minus 2 is 1. Now for a2, all we have to do is substitute 2 into n, and we're going to have 3 times 2, which is 6, minus 2, and we know that 6 minus 2 will give you 4. Next, we are going to find a3. What do we do? As usual, we substitute 3 into n, so we are going to arrive at 3 times 3, which is 9, and 9 minus 2 will give you 7. And last but not the least, for a4, all you have to do is substitute 4 into n, and you arrive at 3 times 4, which is 12, and 12 minus 2 will give you 10 as your answer. And with that, you've gotten your first four terms of the sequence. So next, we're going to start with our 6 examples for this segment. So as you can see, you're told to find an is equals to 2n plus 1, find the first four terms. So as usual, to get the first four terms, all you have to do is substitute 1, 2, 3, and 4 into n. So once you slot in 1 into n, you have a1, and that will be 2 times 1, which is 2, plus 1, and 2 plus 1 is equals to 3. Now for a2, you substitute 2 into n, and you are going to have 2 times 2, which is 4, plus 1, which will give you 5. For you to get a3, you substitute 3 into n, and that will be 2 times 3 plus 1. And we know that 2 times 3 will give you 6. 6 plus 1 will give you 7. Now, a4, you are going to substitute 4 into n, and you multiply 2 times 4 plus 1. And we all know that 2 times 4 is 8, and 8 plus 1 is equals to 9. And with that, you've gotten your first four terms. Now, the next question is an is equals to 5n. Find the first four terms. This is actually very easy. All you have to do, as usual, is just slot in the first four numbers into your n, which is 1, 2, 3, and 4. So for the first one, a1 is equals to 5 times 1, which is 5. For a2, we will have 5 times 2, which is 10. For a3 will have 5 times 3, which will give you 15, and for a4 we have 5 times 4, which will give you 20. For our medium example, we have an is equals to n squared minus n. Find the first four terms. This is also easy and nothing to be worried about, because all you have to do, like we always say, is for you to slot in the first four numbers, since you're looking for the first four terms. And we know the first four numbers are what? 1, 2, 3, and 4. So for a1, when you put in 1 into 1 square minus n, that 1 into n square minus n, you have 1 square minus 1, which is 1 minus 1, which will give you 0. Now when you slot in 2 into n square minus n, you have 2 square minus 2, which will give you 2 squared is 4, minus 2 will give you 2. 4 minus 2 will give you 2. Now for a3, you're going to have 3 square minus 3 when you substitute 3 into n square minus n, and 3 squared is 9. 9 minus 3 will give you 6. And as for a4, all you have to do is substitute 4 into n squared minus n, and you're going to have 4 squared minus 4, which will give you 4 squared is 16, which will give you 16 minus 4, and 16 minus 4 will give you 12. And with that, you have gotten your first four terms. Now for the next medium question, we have an is equals to 2 raised to n minus n. Find the first four terms. So as usual, all we have to do is slot in 1, 2, 3, and 4, since that is the first four terms, into our n. And in this case, our n is 2 raised to n minus n. Still nothing to be worried about. You just have to follow the process. So for a1, when you slot in 1, you are going to arrive at 2 raised to 1 minus 1. 2 raised to 1 will give you 2. 2 minus 1 will give you 1. Now for a2, you slot in 2 in our n, and we're going to have 2 raised to 2 minus 2. 2 raised to 2 will give you 4, and 4 minus 2 will give you 2. Now for a3, all we have to do is substitute 3 into our 2 raised to n minus n, and that will give you 2 raised to 3 will give you 2 times 2, 4, 2 times 4, 8. 8 minus 3 will give you 5. And for a4, which is the last but not the least, all you have to do is substitute 4 in our n, and that will give us 2 raised to 4 minus 4. And 2 raised to 4 is 2 times 2, 4, 2 times 4, 8, 2 times 8, 16, minus 4. And 16 minus 4 will give you 12. And with that, we have gotten our first four terms. Now let's move on to the hard examples. In this case, we have an is equal to n squared divided by n plus 1. find the first 4 terms. So as usual, all you have to do in this case, since you are looking for the first 4 terms, you just list out 1, 2, 3, and 4 and substitute it into n. So for us to get our a1, we are going to have 1 squared divided by 1 plus 1, and we know 1 squared is 1 and 1 plus 1 is 2, so our answer is half, which is 1 over 2, or 0.5. Now for a2, we are going to have 2 squared divided by 2 plus 1. 2 squared will give you 4, and 2 plus 1 will give you 3, so you have 4 divided by 3. So for A3, you have 3 squared divided by 3 plus 1. And 3 squared is 9, 3 plus 1 is 4, and you get 9 divided by 4 as your answer. And for A4, you have 4 squared divided by 4 plus 1, and 4 squared is 16, 4 plus 1 is 5, so your final answer is 16 divided by 5. And with that, you have gotten your first 4 terms. Now for our next example, we have an is equals to minus 1 raised by n multiplied by n squared. Find the first 4 terms. To find the first 4 terms, like I have been saying, all you have to do is list out a of n, 1, 2, 3, up to 4, and start substituting the values into n until you arrive at all your answers. Now for a1, all you have to do is put 1 anywhere you see n. So in this case, you are going to have minus 1 raised to power 1 multiplied by 1 squared. And minus 1 raised to power 1 is minus 1. 1 squared is 1. So 1 times minus 1 will give you minus 1. Now for a2, all you have to do is substitute 2 anywhere you see n. So in this case, you are going to have minus 1 raised to power 2 times 2 squared. So minus 1 raised to power 2 is the same thing as minus 1 times minus 1, which will give you 1. And 2 squared will give you 4. So 4 times 1 will give you 4. As for a3, you are going to substitute 3 everywhere you see n. So in this case, it's going to be minus 1 raised to power 3 multiplied by 3 squared. And we all know that minus 1 times minus 1 is plus 1. Plus 1 times minus 1 will give you minus 1. And 3 squared will give you 9. So 9 times minus 1 will give you minus 9. Now for a4, you are going to substitute 4 everywhere you see n. So that will be minus 1 raised to power 4 multiplied by 4 squared. So minus 1 times minus 1 is plus 1, plus 1 times minus 1 is minus 1, minus 1 times minus 1 will still give you plus 1. And 4 squared is 16, so 16 times 1 will give you 16. So now moving on to the next segment, we have a sequence whose terms alternate in sign. And we can see an example here where we are to find the first 5 terms of the sequence given by an is equals to minus 1 raised by n divided by 2n plus 1. So we are going to solve this on the whiteboard. So as you can see in the example 2, we are working on the sequence whose terms alternate in sign, and the question we are given is an is equals to minus 1 raised by n divided by 2n plus 1. I'm sure you have noticed that it looks similar with what we saw before, but the difference is that the answers are going to alternate in sign. So for us to find the first 5 terms, all we have to do is substitute 1, 2, 3, 4, 5 into n. So for us to find our a1, all we have to do is substitute 1 into minus 1 raised by n and 2n plus 1, and that will give us minus 1 raised by 1, which will give you minus 1, and 2 times 1 plus 1, which will give you 2 plus 1, and you are going to arrive at minus 1 divided by 3 as your final answer. Now for a2, all you have to do is put 2 everywhere you see n, and that will be minus 1 raised by 2, then 2 times 2 plus 1, and we all know that minus 1 times minus 1 will give you 1, and 2 times 2 will give you 4. So your final answer is going to be 1 divided by 4 plus 1, which will give you 1 divided by 5. Now for a3, we're going to slot in 3 everywhere you see n. So that will be minus 1 raised to power 3 divided by 2 times 3 plus 1. And we know that minus 1 times minus 1 is plus 1, and plus 1 times minus 1 will give you minus 1, while 2 times 3 will give you 6. So that will give you minus 1 divided by 6 plus 1, and your final answer will be minus 1 divided by 7. Now for a4, all you have to do is substitute 4 everywhere you see n. So that will be minus 1 raised to power 4 divided by 2 times 4 plus 1. And we know that minus 1 raised to power 4 is same thing as minus 1 times minus 1, which is plus 1, plus 1 times minus 1, which is minus 1, minus 1 times minus 1, which is plus 1, divided by 2 times 4 plus 1, and 4 plus 2 times 4 is 8, 8 plus 1 is 9. Your final answer is 1 divided by 9. Now, to get A5, all you have to substitute 5 everywhere you see n, and that will give you minus 1 raised to power 5 divided by 2 times 5 plus 1. Minus 1 raised to power 5 is the same thing as minus 1 times minus 1 times minus 1 times minus 1 times minus 1, which will give you minus 1. Then 2 times 5 will give you 10, and 10 plus 1 will give you 11. So your final answer will be minus 1 over 11. So now let's look at some simple examples. So first off, we have an is equals to minus 1 raised to power n times n, right, the first 5 terms. So all you have to do is substitute 1, 2, 3, 4, 5 anywhere you see n. So for a1, when you substitute 1, you have what? Minus 1 raised to power 1 times 1, and that will give you minus 1, because minus 1 raised to power 1 is minus 1, and minus 1 times 1 will give you minus 1. Now for A2, you just have to substitute 2 into n, so that will give you minus 1 raised to power 2 times 2. And we know that minus 1 raised to power 2 is the same thing as minus 1 times minus 1, which will give you 1, and 1 times 2 will give you 2. Now for A3, all you have to do is substitute 3 everywhere you see n, and that will be minus 1 raised to power 3 times 3. Minus 1 raised to power 3 is the same thing as minus 1 times minus 1 times minus 1, which will give you minus 1. So minus 1 times 3 will give you minus 3. Now for A4, you have to substitute 4 everywhere you see n, and that will be minus 1 raised to power 4 times 4. Minus 1 raised to power 4 is the same thing as plus 1, because minus 1 times minus 1 times minus 1 times minus 1 will give you 1, and 1 times 4 will give you 4. Now for A5, all you have to do is slot in 5 everywhere you see n. So in this case, we're going to minus 1 raised to power 5 times 5, and minus 1 raised to power 5 is the same thing as minus 1, because minus 1 times itself 5 times will give you minus 1, and minus 1 times 5 will give you minus 5. Now for the next question, we have an is equals to 1 minus 1 raised to power n divided by n, right, the first 5 terms. So as usual, all we have to do is slot in 1, 2, 3, 4, 5 anywhere we see n. So for our A1, we're going to have minus 1 raised to power 1 divided by 1, and this should give us minus 1, because minus 1 raised to power 1 is minus 1, and minus 1 divided by 1 will give you minus 1. So for A2, you are going to have minus 1 squared divided by 2. Minus 1 squared is the same thing as 1 divided by 2, which will give you 1 over 2. And for A3, you are going to have minus 1 cubed divided by 3. Minus 1 cubed is the same thing as minus 1. Minus 1 divided by 3 is your final answer. For A4, you are going to have minus 1 raised to power 4, which is the same thing as 1. And 1 divided by 4 will give you 1 over 4. And your A5 will be minus 1 raised to power 5 divided by 5. And minus 1 raised to power 5 is minus 1. So your final answer is minus 1 divided by 5. So for our next question, we're going to have an is equals to minus 1 raised to power n times n squared divided by n plus 1. Right, the first 5 terms. So as usual, you're going to substitute 1, 2, 3, 4, 5 into n until you arrive at your final answer. So for A1, you're going to have minus 1 raised to power 1 times 1 squared divided by 1 plus 1. And this will give you minus 1 times 1 divided by 1 plus 1. So that should be minus 1 divided by 2. So your answer is minus 1 divided by 2. Now for A2, you're going to have minus 1 raised to power 2 times 2 raised to power 2 divided by 2 plus 1. And this is going to give you minus 1 square, which is what? Minus 1 times minus 1, which is 1. 2 square is going to give you 4. So 4 times 1 will give you 4, and 2 plus 1 will give you 3. So your final answer is 4 divided by 3. Now for A3, you are going to have minus 1 raised to power 3 times 3 squared divided by 3 plus 1. Minus 1 raised to power 3 will give you minus 1 times minus 1 times minus 1, which will give you minus 1. And 3 squared will give you 9. So 9 times minus 1 will give you minus 9 divided by 3 plus 1, which will give you 4. So your final answer will be minus 9 divided by 4. Now for A4, all you have to do is substitute 4 anywhere you see n, and that is going to give you minus 1 raised to power 4 times 4 squared divided by 4 plus 1. So minus 1 raised to the power 4 will give you 1, and 4 squared will give you 16. So 16 times 1 will give you 16, and 4 plus 1 will give you 5. So your final answer is 16 divided by 5. Now your A5 is going to give you minus 1 raised to the power 5 multiplied by 5 squared divided by 5 plus 1. And minus 1 raised to the power 5 is same thing as minus 1, and 5 squared will give you 25. So 25 times minus 1 will give you minus 25, and 5 plus 1 will give you 6. So your final answer is minus 25 divided by 6. So for our next question, we have minus 1 raised to the power n multiplied by 2n minus 1. Write the first 5 terms. So as usual, all you have to do is substitute into n all 1, 2, 3, 4, 5. See, they're asking for the first 5 terms. So for our A1, when you slot in 1, you're going to have minus 1 raised to the power 1 times 2 times 1 minus 1. And minus 1 raised to the power 1 is minus 1. 2 times 1 will give you 2. 2 minus 1 will give you 1. 1 times minus 1 will give you minus 1. Now for A2, you have minus 1 squared multiplied by 2 times 2 minus 1. So minus 1 squared is the same thing as 1, because minus 1 times minus 1 is 1. 2 times 2 will give you 4, and 4 minus 1 will give you 3. So your answer is 3 times 1, which is 3. Now for your A3, you are going to have minus 1 raised to the power 3 multiplied by 2 times 3 minus 1. And we all know that minus 1 raised to the power 3 is the same thing as minus 1 times minus 1 times minus 1, which is minus 1. Multiplied by 2 times 3, which is 6. 6 minus 1 should give you 5. So 5 times minus 1 will give you minus 5 as your answer. Now for A4, we are going to have minus 1 raised to the power 4 multiplied by 2 times 4 minus 1. Minus 1 raised to the power 4 is same thing as minus 1 in 4 places, which will give you 1. Because minus 1 times minus 1 times minus 1 times minus 1 will give you 1. And 2 times 4 will give you 8. 8 minus 1 will give you 7. 7 times 1 will give you 7 as your final answer. Now for A5, you're going to have minus 1 raised to the power 5 multiplied by 2 times 5 minus 1. And we all know that minus 1 raised to the power 5 is the same thing as minus 1. Because minus 1 in 5 places will give you minus 1. So 2 times 5 will give you 10 minus 1. And 10 minus 1 will give you 9. 9 times minus 1 will give you minus 9 as your final answer. So for the next segment, we have Fibonacci sequence, a recursive sequence. And here in the example, we are given the Fibonacci sequence is defined recursively as follows: A0 or A0 is equals to 1, A1 is equals to 1, and AK is equals to AK minus 2 plus AK minus 1, where K is greater than or equals to 2. Write the first 6 terms of the sequence. So let's work that out on the whiteboard. So just like we have been doing, all we have to do is substitute the value for the first 6 terms, which is 1, 2, 3, 4, 5, 6, wherever we find K in this case. We've been working with N, but this time around we're working with K, but it doesn't matter because K or N, whatever the letter, they all represent unknowns. So we are given the condition that K must be greater than or equals to 2. So that being said, since we have our A0 and A1, all we have to do is find A2 up to A5, because since we start from A0, by the time you get to A5, you would have gotten the first 6 terms of the sequence. So from the question, we know that our A0 is equals to 1, and our A1 is also equals to 1. So using the formula AK is equals to AK minus 2 plus AK minus 1, for us to get our A2, all we have to do is substitute 2 anywhere we see K. So that will give us A2 minus 2 plus A2 minus 1. And we know that 2 minus 2 is 0, so we'll have A0 plus A1. And from the question, we know that A0 is equals to 1 and A1 is equals to 1. So therefore, our A2 is equals to 1 plus 1, which will give you 2. Now, to get our A3, we are going to substitute 3 everywhere we see K. So that will be A3 minus 2 plus A3 minus 1. And that will give you A3 minus 2 will give you A1. And A3 minus 1 will give you A2. So we are going to be left with A1 plus A2. And we know that from the question, our A1 is given as 1, and our A2, we solved that earlier, we arrived at 2. So our final answer is going to be 1 plus 2, which will give you 3. So for us to get our A4, we are going to substitute 4 everywhere we see K. And once we do that, we are going to have A4 minus 2 plus A4 minus 1. And we know that 4 minus 2 is going to give us 2. So A4 minus 2 will give you A2, and A4 minus 1 will give you A3. So A2 will give you, we know we arrived at as 2 as our answer for A2, and we arrived at 3 as our answer for A3. So 2 plus 3 will give you 5. Now, to get A5, all you have to do is substitute 5 everywhere you see K. So that's going to be A5 minus 2 plus A5 minus 1. And we know that 5 minus 2 will give you 3, and 5 minus 1 will give you 4. So A3 plus A4. And we know that A3, we got A3 as 3, and we got A4 as 5. So 3 plus 5 is equal to 8. And so therefore, our first 6 terms are written as 1, 1, 2, 3, 5, and 8. So now the next question says write the first 6 terms of the sequence defined by A0 is equals to 2, A1 is equals to 3, and AK is equals to AK minus 2 plus AK minus 1. So since we know our A0 is 2 and our A1 is 3, for us to get A2, all we have to do is substitute 2 everywhere we see K. And once we put 2 in our K, we arrive at the answer. So now when we slot in 2 in the K, you're going to have 2 minus 2, which is 0, and that's A0. Now for the other one, 2 minus 1 will give you 1, and that's A1. So from the question, we know that our A0 is 2 and our A1 is 3. So A2 will give you 2 plus 3, which will give you 5. Now for our A3, all you have to do is substitute 3 everywhere you see K. And once you put your 3 in K, you're going to have 3 minus 2, which is 1. And for the other part, you slot in 3 and you have 3 minus 1, which is 2. So that will be A1 plus A2. And A1 from the question is given to us as 3, and we solved for A2 where we got 5. So our A3 is 3 plus 5, which will give you 8. Now for us to get our A4, all you have to do is substitute 4 everywhere you see K. And when you substitute 4 into K, you're going to have 4 minus 2, which will give you A2. And for the other part, you substitute 4 minus 1, which will give you 3. So A2 plus A3, and we know our A2 is equal to 5, and we solved A3 and we got 8. So our A4 will give you 5 plus 8, which will give you 13. Now to get the A5, all you have to do is substitute 5 everywhere you see K. And when you do that, you're going to end up with 5 minus 2, which will give you 3, and that's how we got A3. And for the other part, substitute 5 minus 1, which will give you 4, which will give you A4. So A3 we got as 8, and A4 we got as 13. So our A5 will give you 8 plus 13, which will give you 21. So our first terms are 2, 3, 5, 8, 13, and 21. So for our next question, we have A0 is equals to 0, and we have A1 is equals to 1, and we are working with AK is equals to AK minus 1 minus AK minus 2. And we are asked to find the first 6 terms of the sequence. So we know we are given our A0 as 0, and we are given our A1 as 1. So since we are looking for the first 6 terms, that means the next numbers we are going to be looking for is A2, A3, A4, A5. So to get our A2, all we have to do is substitute 2 anywhere we see K. So that will be what? 2A, 2 minus 1 minus 2 minus A2 minus 2. So we know that will give us 2A2 minus 1 minus A2 minus 2. So we know that 2 minus 1 will give us 1. So we are left with 2A1, and 2 minus 2 will give 0, and that will be A0. So from the question, we know that A1 is equals to 1, so that will leave us with 2 times 1. And we know that A0 is equals to 0. So 2 times 1 is 2, and 2 minus 0 will give you 2. Now, to get our A3, all we have to do is substitute through 3 anywhere we see K. So that will give us 2A3 minus 1 minus A3 minus 2. And we know that 3 minus 1 will give you 2, and 3 minus 2 will give you 1. So we are going to be left with 2A2 minus A1. And we were able to solve A2 and we got 2. So that means we are going to have 2 times 2. And we know from the question that A1 is equal to 1. So we have 2 times 2 minus 1. And we know that 2 times 2 will give you 4. So 4 minus 1 will give you 3. And that's our A3. Now, to find our A4, all we have to do is substitute 4 everywhere we see K. So what would that leave us with? That would be 2A4 minus 1 and A4 minus 2. So we know that 4 minus 1 will give you 3 and 4 minus 2 will give you 2. So we are left with 2A3 minus A2. And we know that A3 is 3. So that will be 2 times 3 is 6 minus 2, which will give you 4. So our A4 is equals to 4. Now, for our A5, all we have to do is substitute 5 everywhere we see K. So we are going to be left with 2A5 minus 1 minus 2A5 minus 2. And we know that 5 minus 1 will give you 4. So that will be 2A4. And 5 minus 2 will give you 3. So that will be A3. So A4 we solved and we got 4, so that will be 2 times 4. And from our earlier question, we solved A3 to get 3, so that will be 3. So you are left with 2 times 4 minus 3. I know that 2 times 4 will give you 8. So 8 minus 3 will give you 5. So our 4 systems are 0, 1, 2, 3, 4, 5. So in our next question, we're also asked to find the 4 systems of the sequence that is defined by A0 is equals to 1, A1 is equals to 2, and our AK is equals to 2AK minus 1 plus 3AK minus 2. So since we are given our A0 as 1 and our A1 as 2, all that simply means is the next term we're going to be looking for is our A2. Now, how do we find our A2? All we have to do is substitute 2 everywhere we have K and solve to get our answer. So in this case, 2 minus 1 and 2 minus 2. So that's going to leave us with A2, that will leave us with 2A2 minus 1 plus 3A2 minus 2, and that will give us 2A1 plus 3A0. And we know that A1 is 2 and our A0 is 1. So that will be 2 times 2 plus 3 times 1, and 2 times 2 is 4, 3 times 1 is 3, and that will give us 4 plus 3, which will give you 7. Now for our A3, all we have to do is substitute 3 everywhere we have K, and that will give us 2A3 minus 1 plus 3A3 minus 2, and that will leave us with 2A2 plus 3A1. And we know that our A2 is 7 and our A1 is 2, so that is going to leave us with 2 times 7 plus 3 times 2. So 2 times 7 will give you 14 plus 3 times 2, which will give you 6. So 14 plus 6 will give you 20. Now, for us to find our A4, all we have to do is substitute 4 everywhere we have K. So that will give us 2A4 minus 1 plus 3A4 minus 2. And we know that 4 minus 1 will give you 3, and 4 minus 2 will give you 2. So that will leave us with 2A3 plus 3A2. And we know that our A3 is 20, we just saw for it. And our A2 is 7, we saw for that earlier. So that will be 2 times 20 plus 3 times 7. So that will give you 40 plus 21. That means our A4 is equals to 61. Now, for us to get our A5, all we have to do is substitute 5 everywhere we have K, and that will leave us with 2A5 minus 1 plus 3A5 minus 2. And we know that 5 minus 1 is 4, and 5 minus 3 is 2. And we know we solve for A4, which gave us 61, and we solve for A3, which gave us 20. So that's going to leave us with 2 times 61 plus 3 times 20. And 2 times 61 is 122. 3 times 20 is 60. So 122 plus 60 will give you 182. So our 4 systems are 1, 2, 7, 20, 61, and 182. So for our next question, we have A naught is equals to 1, A1 is equals to 3, and AK is equals to 2AK minus 1 plus A squared K minus 2. And we are asked to find the 4 6 terms of the sequence. So since we know our A naught is equals to 1, and we know that our A1 is also equals to 3, what we need to look for now is A2, A3, A4, and A5. So to get our A2, all we have to do is substitute 2 everywhere we find our K. So in this case, we have 2A, 2 minus 1, which will give you 2A1. Then in the other place, we have A2, 2 minus 2, which will give you A naught squared. So we know from our question that A1 is equal to 3, so we have 2 times 3, plus we have A naught squared, and we know our A naught is 1, so that will be 1 squared. So 2 times 3 is 6, 1 squared is 1, so our A2 will give you 6 plus 1, which will give you 7. Now, our A3 is equals to 2 times A3 minus 1, which will give you 2A2, plus 2 plus A squared 3 minus 2, which is A squared 1. So that will leave us with 2 times A2, which we got as 7, which is 2 times 7. And we know our A1 is equals to 3, so it will be 3 squared. So 2 times 7 will give you 14, and 3 squared will give you 9. So 14 plus 9 will give you 23. So now, to get our A4, we are going to substitute 4 everywhere we see K. So that will be 2 times A4 minus 1, which should give you 2A3, plus A squared 4 minus 2, which will be A2 squared. So that will give you 2 times, we know our A3 is 23, so that's 2 times 23, plus we know our A2 is 7, so that will be plus 7 squared. So 2 times 23 will give you 46, plus 7 squared, which is 49. So 46 plus 49 will give you 95. Now, for us to get our A5, all we have to do is substitute 5 everywhere we see K. So we know that 5 minus 1 will give you 4, and for the other part, we are left with A squared 5 minus 2, which will give you A3 squared. So we know that our A4 is 95 from what we just saw, so that will be 2 times 95, plus we know that our A3 is equals to 23, so that will be plus 23 squared, which will give you 190 plus 529, which will give you 719. So our 4 6 terms are 1, 3, 7, 23, 95, and 719. So our next question, we have A naught is equals to 2, our A1 is equals to 5, and our AK is equals to 3AK minus 1 minus AK minus 2, and we are told to find the 4 6 terms. Since we know our A naught is equals to 2, and our A1 is equals to 5, and AK is equals to 3AK minus 1 minus AK minus 2, what we need to look for next is our A2. So what we have to do is substitute 2 everywhere we have K. So that will give you 3A2 minus 1, which will give you 3A1. And for the other side, we have AK minus 2. So that will be A2 minus 2, which will give you A0. So 3 times A1, we know our A1 is 5. So 3 times 5 will give you 15, and minus A naught, which our A naught is 2 from the question. So 15 minus 2 will give you 13. Now our A3, all you have to do is substitute 3 everywhere you have K. So that will be 3 times A3 minus 1, which will give you 3A2, minus A times 3 minus 2, which will give you A1. So that will give you 3 times 13 minus, we know our A1 is 5. So 3 times 13 is 39, minus 5 will give you 34. Now for our A4, all you have to do is substitute 4 everywhere you have K. So that will be what? 3 times A4 minus 1 minus A4 minus 2. And we know that 4 minus 1 will give you A3. So we have 3 times A3 minus A2, and we know our A3 is 34, and our A2 is 13. So that will be 3 times 34, which is 102 minus 13, which will give you 89. Now to get our A5, all you have to do is substitute 5 everywhere you find your K. So that will give you 3A, 5 minus 1 will give you 4, and 3A 5 minus 2 will give you 3. So that's 3A4 minus A3. And we know our A4 is 89. So 3 times 89 will give you 267 minus 34, which will give you 223. So our 4 6 terms are 2, 5, 13, 34, 89, and 233. So for our next question, we have A naught is equals to 4, A1 is equals to 2, and AK is equals to AK minus 1 squared minus AK minus 2. So all we have to do is to find, since we are given A naught and A1, we need to find A2, A3, A4, and A5, since they asked us to write the first 6 terms. So we just have to do what we have been doing since. For us to get our A2, all you have to do is substitute 2 everywhere you see K, which is actually very, very simple. So we know our A naught is 4, and we know that our A1 is 2. So to get our A2, all we have to do is to start substituting 2 into K. So we will start with A2, 2 minus 1, which will give you 1, and A2 minus 2, which will give you A naught. So that's A1 squared minus A naught. And we know that our A1 is 2, so 2 squared is 4, and 4 minus 4 will give you 0. Now for our A3, we will substitute 3 everywhere we have K. So that will be A3 minus 1, which is 2, so that's A2 squared minus A1. How did we get A1? 3 minus 2 will give you 1. So A2 squared is what? That's 0 squared minus 2. So that will give you minus 2. Now for our A4, we have 4 minus 1, which will give you 3. So that's A3 squared minus A4 minus 2, which is A2. So A3 is minus 2. So minus 2 squared will give you plus 4. So 4 minus 0 will give you 4. Now our A5 is A equals to A4 squared minus A3. So A4 squared will give you 4 squared minus 2. So 4 squared will give you 16, then minus times minus 2 will give you plus 2. So 16 plus 2 will give you 18. So our 4 6 terms are 4, 2, 0, minus 2, 4, and 18. So the next segment is factorial notation, and some very important sequences in mathematics involve terms that are defined with special types of products called factorials. Definition of factorial: if n is a positive integer, n factorial is defined as n factorial, which is equals to 1 times 2 times 3 times 4 times and so on up to n times n minus 1 times n. And as a special case, 0 factorial is defined as 0 factorial is equals to 1. Now, here are some values of n factorial for the first several non-negative integers. Notice that 0 factorial is 1 by definition. So as you can see, 1 factorial is equals to 1, 2 factorial is 1 times 2, which is equals to 2, 3 factorial is 1 times 2 times 3, which is equals to 6, 4 factorial is 1 times 2 times 3 times 4, which is equals to 24, and 5 factorial is 1 times 2 times 3 times 4 times 5, which is 120. The value of n does not have to be very large before the value of n factorial becomes extremely large. For instance, 10 factorial is equals to 3,628,800. Factorials are denoted by n factorial, and they are the product of all positive integers from 1 to n, and they are commonly used in permutations, they're used in combinations, and also in advanced calculations. So from our original material, we found out that n factorial is equals to n times n minus 1 times n minus 2 and so on until we got to 1. And we also remember that 0 factorial is equals to 1. So we move on to applications in combinatorics. And combinatorics actually talks about permutations and combinations. So for permutations, we are simply talking about the number of ways to arrange R objects from a group of N objects. So the formula for finding that will be capital letter P N R, which will give you N factorial divided by N minus R factorial. When it comes to combinations, we are actually looking for the number of ways to choose R objects from N objects. And the formula for finding that is capital letter Cn of R, which will give you n factorial divided by R factorial multiplied by n minus R factorial. So now let's look at a question that says, how many ways can 4 books be arranged on a shelf? So using the formula Pn of n, which is n factorial, we have 4 factorial, and we know that 4 factorial will simply give us 4 times 3 times 2 times 1, which will give you 24. So therefore, there are 24 ways to arrange the books. So moving on to the next question, we have find the value of 5 factorial. So this is a very simple question to start things off. So to get 5 factorial, that's actually very easy. That's 5 times 4 times 3 times 2 times 1. And when you multiply 5 times 4 times 3 times 2 times 1, you end up with 120. So the value is 120. So now the next question says, how many ways can 3 people be seated in a row? So for this question, we use n factorial, which is in this case 3 factorial, because our n is 3. So 3 factorial will give you 3 times 2 times 1, which is equal to 6, and the answer is 6 ways. So the next question asks, how many ways can 6 students be seated in a row if 2 specific students must sit together? So for this question, let's treat the 2 students who must sit together as a single block. Now, if you look at that, that means this gives us 5 blocks to arrange. And since we have 5 blocks to arrange, we are going to have 5 factorial. And 5 factorial will give us 5 times 4 times 3 times 2 times 1, which will give you 120. Now, within the block, the 2 students can be arranged in 2 factorial ways. That means 2 people that will sit together can actually be seated AB or BA. So that's 2 factorial, which will give you 2 times 1, which will give you 2. So since we've gotten our the ways the 2 students can sit as 2, and we have gotten the block as 5 factorial, which is 120, the total arrangement is going to give us 5 factorial times 2 factorial, which will give you 120 times 2. And 120 times 2 will give you 240. So that means there are 240 ways. So now, in the next question, we're asked how many ways can 5 letters be selected and arranged from the word games? Now, if you look at the letters, you find out that all of them are unique. So since all 5 letters are distinct, this is a simple permutation of 5 items. So using our notation of P5 of 5, you get 5 factorial, which will give you 5 times 4 times 3 times 2 times 1. So when you multiply 5 times 4 times 3 times 2 times 1, you end up with 120. So therefore, there are 120 ways. So the next question is asking us how many ways can 8 people be seated around a circular table. And for finding circular arrangements, the formula we're going to use is n minus 1 factorial. So since they're asking for how many ways 8 people can be seated, we're going to have 8 minus 1 factorial. And this will give you 7 factorial. And 7 factorial will give you 7 times 6 times 5 times 4 times 3 times 2 times 1. And this will give you 5040. So that means there are 5040 ways for 8 people to be seated around a circular table. So our next question, we are asking how many ways can a committee of 4 members be formed from a group of 10 people if 2 specific people must always be included? Since 2 people must be included, we only need to choose 2 additional members from the remaining 8 people. I go over that again. Since 2 specific people must be included, we only need to choose 2 additional members from the remaining 8 people. So now, how do we write this out? This will be written in notation form as C82, which will give you 8 factorial divided by 2 factorial multiplied by 8 minus 2 factorial. So this will give us 8 times 7 divided by 2 times 1. In case you're wondering how they arrived at that, 8 factorial is the same as 8 times 7 times 6 factorial, while 8 minus 2 is 6 factorial. So 6 factorial will cancel out 6 factorial. And that's how they arrived at 8 times 7 divided by 2 times 1. Don't forget, 2 factorial is the same as 2 times 1. So 8 times 7 will give us 56, and 56 divided by 2 will give you 28. So there are 28 ways to form the committee. So for the next segment, we have writing in terms of a sequence involving factorials. And you can see an example here where we are told to write the first 5 terms of the sequence given by an is equals to 2 raised by n divided by n factorial. So let's solve it on the whiteboard. So in this question, we have an is equals to 2 raised by n divided by n factorial. And we are asked to find the first 5 terms of the sequence. So all we have to do is just to substitute the value, the first 5 terms into our n to get the values. So once you put in 0, since 0 factorial can have a value, you are going to have for a naught 2 raised by 0 divided by 0 factorial, and that will give you 1 divided by 1, which is equals to 1. Now to get a1, that will be 2 raised by 1 divided by 1 factorial, which will give you 2 divided by 1, which is equals to 2. Now to get a2, you slot in 2 wherever you see n, and that will give you 2 raised by 2 divided by 2 factorial, and this will give you 4 divided by 2, which is equals to 2. Now to get your a3, you slot in 3 everywhere you find an n, and that will give you 2 raised by 3 divided by 3 factorial, and this will give you 8 divided by 6, because 2 times 3 will give you 6, and that will give you 4 divided by 3. Now to get a4, which is our last term, you substitute 4 everywhere you get c and n, and that will be 2 raised by 4 divided by 4 factorial, and this will give you 16 divided by 24, which will give you 2 divided by 3. So our next question, we have an is equals to n factorial divided by n. Find the first 5 terms. So to get our first 5 terms, we're going to substitute certain values. In this case, we started with a1, because if you divide 0 factorial by 0, that will give you a value. So when we use 1, we're going to have 1 factorial divided by 1, which will give you 1, and 8 will give you 2 factorial divided by 2, which will be 2 divided by 2, which will give you 1. Now a3 will give you 3 factorial divided by 3, which will give you 6 divided by 3, and that will give you 2. Now a4 will give you 4 factorial divided by 4, and that will give you 2 times 3 times 4, which will give you 2 times 3, 6. 6 times 4 will give you 24 divided by 4, and that will give you 6. Now, a5 will give you, you substitute 5 everywhere you get cn, so that will be 5 factorial divided by 5. And 5 factorial will give you 120, so that will be 120 divided by 5. And 120 divided by 5 will give you 24. So for the next question, we have an is equal to n factorial. Find the first 5 terms. So this is actually a very simple question. All we have to do is just to put the first 5 terms into n for us to arrive at our answer. So 1 factorial is equals to 1, 2 factorial is equals to 2, 3 factorial is equals to 6, that's 2 times 3 will give you 6, and 4 factorial will give you 2 times 3 times 4, which is 24, and 5 factorial will give you 420. So for our next question, we have an is equal to n plus 1 factorial divided by n factorial. Find the first 5 terms. So all we have to do is substitute the value of whatever we're looking for into n so that we can arrive at an answer. So for A1, you just slot in 1 anywhere you find n, and that will give you 1 plus 1 factorial, which is 2 factorial divided by 1 factorial. So that will be 2 factorial divided by 1 factorial, which is equal to 2 times 1 divided by 1. And 2 divided by 1 will give you 2. So A2 will give you 2 plus 1 divided by 2 factorial, and this will give you 3 factorial divided by 2 factorial. And we know that 3 factorial is 3 times 2 times 1, and 2 factorial is 2 times 1. So this will give you 2 times 3, which is 6, divided by 2, which will give you 3. So our A3 will give you 3 plus 1 factorial divided by 2 factorial. And we know that 3 plus 1 is 4 factorial, and 4 factorial will give you 4 times 3 times 2 times 1, which will give you 2 times 3, 6, 6 times 4, 24. So 24 divided by 2 times 3, which is 6, will give you 24 divided by 6, which will give you 4. Now A4 will give you 4 plus 1 factorial divided by 4 factorial. And 4 plus 1 factorial will give you 5 factorial. And we know that 5 factorial is 120. And we know that 4 factorial will give you 2 times 3, which is 6 times 4, which is 24. So 120 divided by 24 will give you 5. Now for A5, we give you 5 plus 1 factorial divided by 5 factorial. So 5 plus 1 factorial will give you 6 factorial divided by 5 factorial. And you know that 6 factorial is same thing as 6 times 5 factorial. So 5 factorial will cancel out 5 factorial, and the final answer will be 6. So the next question we are looking for, an is equals to 2n factorial divided by n factorial. Find the first 5 terms. So all we have to do is substitute the value of a1 to 5 to get our first 5 terms. So for the first one, we have 2 times 1, which is 2 factorial divided by 1 factorial. 2 times 1 factorial, 2 times 2 factorial is 2 times 1, which is 2, and 1 factorial is 1 times 1, which is 1. So 2 divided by 1 will give you 2. Now A2 will give you 2 times 2 factorial divided by 2 factorial. So 2 times 2 is 4. 4 factorial divided by 2 factorial. And we know that 2 factorial can cancel out 2 factorial, so I left with 4 times 3. And 4 times 3 will give you 12. Now to get A3, you are going to multiply 2 by 3. So that will give you 6 factorial divided by 3 factorial. So we know that 6 times 4 times 3 factorial can cancel out 3 factorial. So you are left with 6 times 5 times 4, since 3 factorial will cancel out 3 factorial. So we are left with 6 times 5 times 4. And 6 times 5 times 4, 4 times 5 will give you 20. 20 times 6 will give you 120. Now to get A4, we have to substitute 4 everywhere we see n. So that will be 2 times 4 factorial divided by 4 factorial. So that will give you 8 factorial divided by 4 factorial. So that will be 8 times 7 times 6 times 5 times 4 factorial. We'll stop with 4 factorial since 4 factorial can cancel out 4 factorial. So 8 times 7 times 6 times 4 will give you 1680. Now for A5, all you have to do is substitute 5 everywhere you see n. So that will be 2 times 5 factorial divided by 5 factorial. So 2 times 5 factorial is same thing as 10 factorial. So we have 10 factorial divided by 5 factorial. So this will be 10 times 9 times 8 times 7 times 6 times 5 factorial, and 5 factorial cancel out 5 factorial. So now you have 10 times 9 times 8 times 7 times 6, which will give you 30,240. So for the next question, we have an is equals to n factorial squared divided by n plus 1. Find the first 5 terms. So in this case, for the first 5 terms, we are going to substitute the value of 1, 2, 3 up to 5. So for A1, once you substitute 1, you have 1 factorial, which is the same thing as 1. So 1 squared is the same thing as 1. And the denominator is going to be 1 plus 1, which is 2. So 1 divided by 2, you are left with 1 over 2. Now for A2, you are going to have 2 factorial squared divided by 2 plus 1. And 2 factorial squared will be 2 times 1, which is 2, so 2 squared will give you 4. And the denominator is 2 plus 1, which is 3, so that's 4 divided by 3. Now, for A3, you're going to have 3 factorial squared divided by 3 plus 1, and that will give you 3 factorial, which is 2 times 3 is 6 squared divided by 4, and 6 squared is 36, so you're going to be left with 36 divided by 4. Now, for A4, you're going to have 4 factorial squared divided by 4 plus 1, and that will give you 4 times 3 times 2 times 1, which will give you 24 squared divided by 5. And 24 squared will give you 576 divided by 5. And 576 divided by 5 will give you 105.2. Now for our A5, you're going to have 5 factorial squared divided by 5 plus 1, and this will give you 14,400 divided by 6, and that will give you 2,400. Now for our next question, we have an is equals to 2 raised to power 2n divided by n factorial squared. Find the first 5 terms. So this is a little bit technical, but still very easy. So to find our first 5 terms, we just have to substitute 1, 2, 3, 4, 5 in our n. So for our A1, once you substitute 1 into n, you end up with 2 raised to power 2 times 1 divided by 1 factorial squared. So that will give you 2 raised to power 2, which is 4, divided by 1, which will give you 4. Now for our A2, you're going to have a raised to power 2 times 2 divided by 2 factorial squared. And this is going to give you 2 raised to power 4 divided by 2 factorial squared. Now 2 raised to power 4 is 16, and 2 factorial squared is 4, because 2 times 1 is 2, and 2 raised to power 2 is 4. So 16 divided by 4 will give you 4. Now for our A3, you have 2 raised to power 2 times 3 divided by 3 factorial squared. And 2 times 3 will give you 6. And 2 raised to power 6, 2 raised to power 6 is going to give you 64. And 3 factorial squared is the same thing as 2 times 3 is 6 squared, and 6 times 6 is 36. So 64 divided by 36 will give you 16 divided by 9. Now, our A4 will give you 2 raised to power 2 times 4 divided by 4 factorial squared, and that will give you 2 raised to power 8 divided by 4 times 2 times 3 squared. So 2 raised to power 8 is going to give you 256. And 2 times 3 times 4 is 24. So 24 squared will give you 576. So 256 divided by 576 will give you 64 divided by 144. And that can be further broken down into 4 divided by 9 as the answer for A4. Now for A5, we're going to have 2 raised to power 2 times 5 divided by 5 factorial squared. Now 2 raised to power 2 times 5 will give you 2 raised to power 10. And 5 factorial squared is the same thing as 5 times 4 times 3 times 2 times 1, which is 120 squared. So 2 raised to power 10 is the same thing as 1024, and 120 squared is the same thing as 14,400. So this will give you 64 divided by 900, which can further broken down to 16 divided by 225. So now we move on to summation notation. So definition of summation notation. There is a convenient notation for the sum of terms of finite sequence, and it's called summation notation or sigma notation because it involves the use of the uppercase Greek letter sigma, written as shown on the screen. Now, the sum of the first n terms of a sequence is represented by sigma n ai with I equals to 1 for a1 plus a2 plus a3 plus a4 plus and so on up to a of n, where I is called the index of summation, n is the upper limit of summation, and 1 is the lower limit of summation. So we are given some questions here, and we have to find the sum for each of them. You can see the first one, A, we have 3i, and we sum it from 1 to 5. We have 1 plus k squared, where k starts with 3, and we sum up to 6. And we have for 1 divided by I factorial, where I starts with 0, and we sum it up to 8. So we are going to solve a lot of questions, but let's look at how these ones were solved. So for the first one, all you have to do is just substitute 1 up to 5 everywhere you see I, and you sum them. So in this case, once you put 1 in I, you're going to have 3 times 1, 3 times 2, 3 times 3, 3 times 4, 3 times 5. But in this case, they brought out 3 since 3 is common, and they added 1, 2, 3, 4, 5, and it got 15, and 3 times 15 will give 45. Now for the other one, since k starts from 3, you substitute 3 in all of k, then you sum it and you stop at 6. So in this case, you have 1 plus 3 squared plus 1 plus 4 squared plus 1 plus 5 squared plus 1.6 squared. So when you solve that, you're going to have 10 plus 17 plus 26 plus 37, and when you sum that, you get 90. So for the last one, all you have to do is substitute from 0 up to 8 in all the value of I. So once you do that, you have 1 over 0 factorial plus 1 over 1 factorial, like that, up to plus 1 over 8 factorial. And when you sum that, you're going to end up with 2.71828. So here are a couple of properties of sums that you should be aware of. I will still go into detail later on, but I just want to cover the material you already have access to. So you have where C is a constant, you have the summation as C of n, and where C is a constant, you can also see here that you can take out the constant just behind the sigma notation. And when you have AI plus BI, you can actually separate them and assign sigma properties to both of them. And same thing when there is a difference. So it applies both to addition and subtraction. But like I said, I will go into more details and show you more techniques you can use to make your life a whole lot easier. Okay, so let's go over the properties one more time, and I'm going to add some other new ones that are going to be necessary that we're going to use down the line. So like I mentioned earlier, when you have something like AI plus BI, you can separate them and assign separate sigma to both of them, sigma properties to both of them. And like I also alluded to earlier, when you have a constant times AI, you can remove the constant and find the summation and then multiply it by the constant. So this property is what is known as linearity under the properties of summation. Please don't forget, C in this case stands for constant. We also have special summation formulas. And the first one is the sum of the first n integers. And for that case, when you have I for I equals to 1 up to n, you can write it in the form of n multiplied by n plus 1 divided by 2. Now, the second special summation formula is the sum of the first n squares. And for that one, when you have I squared and you have to find the summation, you can write in the form of n times n plus 1 times 2n plus 1 divided by 6. Last but not the least, we have sum of the first n cubes. So in this case, when you have I3, you can write it in the form of n times n plus 1 divided by 2 squared. So now let's look at some questions so that we can better understand some of those properties. So in this case, we have 2i plus 3, and we have to sum it from I equals to 1 to 5. So all we have to do is substitute 1 everywhere we see I, and we sum it up to 5. So for the first one, you are going to put 1 in I, and that will be 2 times 1 plus 3. For the second one, you are going to put 2 in I, that's 2 times 2 plus 3. For the third one, you are going to put 3 in I, and that will be 2 times 3 plus 3. And for the fourth one, you are going to put 4 in I, and that is 2 times 4 plus 3. And for the last one, you are going to put 5 in I, and that's 2 times 5 plus 3. And this will give you 5 plus 7 plus 9 plus 11 plus 13, and total will give you 45. So for the next question, we have 3i plus 1, and we have to evaluate I equals 1 up to 4. We'll sum that. So when you substitute 1 in I, you are going to have 3 times 1 plus 1. When you substitute 2 in I, you are going to have 3 times 2 plus 1. And when you substitute 3 in I, you are going to have 3 times 3 plus 1. And when you substitute 4 in I, you are going to have 3 times 4 plus 1. 3 times 1 is 3, 2 times 3 is 6, 3 times 3 is 9, and 3 times 4 is 12. So that will leave you with 3 plus 1, 4, 6 plus 1, 7, 9 plus 1, 10, and 12 plus 1, 13. And when you sum 4 plus 7 plus 10 plus 13, you are going to end up with 34. So next we have summation of I equals to 1 up to 6 for I squared. So since we have I squared, we can apply one of the properties of summation. So if you recall, when you have I squared, you can write it in the form of n times n plus 1 times 2n plus 1 divided by 6. So since we are going to find I equals to 1 up to 6, which is n in this case, all you have to do is substitute 6 everywhere you find n. So once you substitute 6, you are going to have 6 times 6 plus 1 times 2 times 6 plus 1 divided by 6. And 6 plus 1 will give you 7, and 2 times 6 will give you 12. 12 plus 1 will give you 13, and we know 6 can cancel out 6. So you are going to be left with 7 times 13, and 7 times 13 will give you 91. So you can actually use the other method, which is easier to use when you have smaller n. So in this case, since we just have 6, and I squared is actually a very simple form, we can actually use that method. So when you substitute 1 up to 6 in I squared, you're going to have 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared plus 6 squared. And this is going to give you 1 plus 4 plus 9 plus 16 plus 25 plus 36, and this will give you 91. So in this question, we are given I squared plus 2i, and we have to sum it from I equals to 1 up to 5. So if you look at this question very well, you will notice that you can actually split the sum. And what does split the sum mean? Split the sum means that you can actually separate it using the properties I mentioned earlier. So if you are to separate this, what are you going to end up with? You're going to end up with summation of I equals 1 to 5 for I squared plus summation I equals to 1 up to 5 for 2i. So now, once you put it this way, don't forget, we have a way of writing I squared when it is solved, and that is what? That's n times n plus 1 times 2n plus 1 divided by 6. So in this case, our n is 5, so that will be 5 times 5 plus 1 That is 2 times 5 plus 1 divided by 6. I know that 5 plus 1 is 6. So you have 5 times 6 times 2 times 5, which is 10 plus 1, 11. 6 can cancel out 6, so you are going to end up with 5 times 11, which will give you 55. Now, for us to find the other part of the sum, we know that 2i, we can sum I equals to 1 up to 5 for 2i, and 2 is a constant, so we apply another property of linearity. So the constant 2 can go outside, and now that we now have summation of I equals to 1 up to 5 for I, we can actually apply the other rule that says n times n plus 1 divided by 2. So we know our n is 5, so that will be 5 times 5 plus 1 divided by 2. And 5 plus 1 is 6. And we all know that 2, which is the denominator, can cancel out the other 2. So when 2 cancel out 2, you are left with 5 times 6. And 5 times 6 will give you 30. So for us to get our final answer, all we have to do is add the separate parts together, the answer to the separate parts together, and we'll arrive at our answer. So the final answer for the summation of I equals to 1 is for 5 will give you 55 plus 30. 55 plus 30 will give you 85. So let us apply the second method, because we are summing up to 5, so it shouldn't be hard to solve since it's 5. So all we have to do is just substitute 1 up to 5 anywhere we find I. So for the first one, you put 1 squared plus 2 times 1. The next one, you put 2 squared plus 2 times 2. For the next one, you put 3 squared plus 2 times 3. And for the fourth one, you put 4 squared plus 2 times 4. And for the next one, you put 5 squared plus 2 times 5. Now, when you open this, what do you end up with? You end up with 1 squared plus 2 is same thing as 1 plus 2, which is 3. Now, for the next one is 2 squared plus 2 times 2, which is the same thing as 4 plus 4, which is 8. For the next one, you have 3 squared plus 2 times 3, which is the same thing as 9 plus 6, which is 15. For the next one, you have 4 squared plus 2 times 4, which will give you 16 plus 8, which is 24. And last but not the least, you have 5 squared plus 2 times 5. And 5 squared is 25 plus 2 times 5, which is 10, which is 35. So when you add 3 plus 8 plus 15 plus 24 plus 35, you end up with 85. So now for this example, we have a larger number, which is 10. And we are to sum I equals to 1 up to 10 for 4i minus 2. So we can also apply the property of separating it and assigning sigma to both parts. So doing that, you're going to have I equals to 1 summed up to 10 for 4i, and I equals to 1 summed up to 10 for 2. So using the law of linearity, we can take the 4, which is a constant, out of the sigma. And now we can now solve for summation of I equals to 1 up to 10 for I. And don't forget, we have a formula for that, which is n times n plus 1 divided by 2. So we have 5 times 10 plus 1, which is 11, divided by 2. So 2 in 10 is going to give you 5, and 5 times 11 will give you 55. So you have 4 times 55. Now for us to solve the other side, we know that 2 is alone, but don't forget, I raised to power 0 is the same thing as 1. So we are going to convert 2 times 1, the 1 that is not shown here, we can convert it to I raised to power 0. So when you convert it to I raised to power 0, all you have to do is to slot in 1 up to 10. So then we are going to have 2 times 1 raised power 0, 2 times 2 raised power 0, 2 times 3 raised power 0, up to 2 times 10 raised power 0. And you realize that when you do that, you're going to end up with 2 in 10 places. But once 1 raised power 0 is 1, 2 raised power 0 is 1, 3 raised power 0 is 1. So you are going to end up with 2 in 10 places. So that will be 2 plus 2 plus 2 plus 2 plus 2 like that until you end up with 20. So now that we've gotten the second part as 20, we can actually sum all parts together. So we remember we ended up with 4 times 55 for the first part, and now at subtract 20. So 4 times 55 will give you 220, and 220 minus 20 will give you 200. You can see that this method is best suited for large numbers, because if you were to substitute 1, 2, 3 up to 10 into I, it will take a very long time for you to arrive at your answer. So now for this question, we have I equals to 1 summed up to 8 for I cubed minus I squared. So there's actually nothing to be worried about. All we have to do is apply the same logic we've been using from the start. So first off, we're going to split it. So once you split it, you're going to have I3, where I is equals to 1 summed up to 8, minus I2, where I is equals to 1 summed up to 8. And when you put it that way, we can start applying some of the properties we mentioned earlier. We know that I3 will give you n times n plus 1 divided by 2 squared. So in this case, our n is 8, so you are going to end up with 8 times 8 plus 1 divided by 2, and 8 plus 1 is 9. So you are going to have 8 times 9 divided by 2 squared, and that will give you 36 squared. And 36 squared will give you 1296. Now for the other part, we know that we're working with I squared. And for I squared, you're going to end up with n times n plus 1 times 2 times n plus 1 divided by 6. So in this case, since our n is 8, we're going to end up with 8 times 8 plus 1 times 2 times 8 plus 1. And we know that 8 plus 1 is 9. And we also know that 2 times 8 plus 1 is same thing as 16 plus 1, which is 17. So we are left with 8 times 9 times 17 divided by 6, which will give you 204. So now when we bring it all together, we're going to end up with 1296 minus 204, which will give you 1092. So next we have evaluate 5I squared plus 3I minus 4, where I is equals to 1 summed up to 15. So as you can see, if we were to use that our simple method, it will take forever to solve something like this, unless if you have maybe a calculator or something. But solving manually will take a long time. So now, using the properties we're given at the beginning, we know that we can separate each, we can split it. So once you split it, you know that 5 is a constant, so we can apply linearity and take the 5 outside the sigma. So you start with 5 sigma 15I equals to 1 I squared plus 3, which is also a constant, so we can apply linearity, times summation I for I equals to 1 up to 15 minus sigma 4I equals to 1 up to 15. So now when you do that, our I2, don't forget, is we can be broken down to n times n plus 1 times 2n plus 1 divided by 6. So in this case, our n is 15. So when you substitute 15, you're going to have what? 15 times 15 plus 1 times 2 times 15 plus 1. 15 plus 1 is 16. So you're going to have 15 times 16 times 2 times 16 plus 1, which is 31. 2 times 15 plus 1, sorry, which is 30 plus 1, which is 31. So 15 times 16 times 31 divided by 6 will give you 1240. Now for the other part, we're going to have summation of I, where I is equals to 1 up to 15, and we know that we can write in the form of n times n plus 1 divided by 2. So in this case, we are going to have 15 times 15 plus 1 divided by 2. So that will give you 15 times 16 divided by 2. So we know that 2 in 16 is 8, and 8 times 15 give you 120. So for the last part, you have summation of 4 for I equals to 1 up to 15. So in this case, we are going to have, like I explained in an earlier example, you know that I naught is the same thing as 1. So since there's an imaginary 1 there, we can put I naught there and put 1 to 15. So in this case, it's going to be 4 in 15 places. So that's 4 times 15, which will give you 60. So when we bring everything together, we're going to end up with 5 times 1,240 plus 3 times 120 minus 60. 5 times 1,240 will give you 6,200 plus 3 times 120 will give you 360 minus 60. So your final answer is 6,500. As we conclude this portion of our discussion on sequence and series, I hope you found the information both enlightening and thought-provoking. We've explored segments such as writing in terms of a sequence, sequence with alternating signs, recursive sequence, factorial notation, summation notation, and properties of summations. And we've also looked at some real-world examples of sequence and series. However, our journey doesn't end here. In our next session, we'll delve deeper into arithmetic and geometric sequences, some of a series, just to mention a few. We'll examine applications to business and finance with examples from areas like price, money, and total sales. I encourage you to reflect on what we've learned today, and thank you for your attention and engagement. I look forward to continuing this exploration with you. Bye.